as solar cycle 25 is now getting underway, we are reminded that all of humankind's space missions, including the International Space Station and much of our nation's infrastructure in communication, surveillance, and navigation, including the critically important GPS GNSS system, are operating in this environment created and driven directly by the sun's emissions. Given all of the identified needs, a win-win situation is to develop various predictive capabilities that extract maximum value from scientific data through developing new approaches from combining data-driven methods, modeling, and algorithms capable of machine learning, deep learning, even in the face of limited, weak descriptions or identifications of physical elements and features. That is what the two heliophysics teams are tackling in FDL this year. The first one, the Sun as a fully resolved star. It takes days to build up solar emissions measurements across the Sun's full spherical 4π surface, and the result is an historical amalgam of the Sun. Solar structures change significantly within hours, and therefore a fully resolved 4π instance of the Sun requires measurement of solar irradiance across the full surface simultaneously. The resulting 4π data product will provide a valuable data product for solar and stellar studies and improve the forecast of space weather.
My name is Benoit, and my colleagues and I will provide an overview of our project titled 4π EUV Irradiance, the Sun as a Star. For this presentation, other than myself, you'll also be hearing from our amazing researchers Mira, Robert, and Margarita. The story I want to tell about the Sun is one of perspectives. The Sun drives all life on Earth, but it is also the hazard that our satellites and astronauts have to live with every day. For example, the extreme ultraviolet light, or EUV, that the Sun emits affects Earth's atmosphere in such a way that it degrades the orbit of the 40,000 or so satellites in low Earth orbit, with the risk of making them fall and burn in Earth's atmosphere. Therefore, we need to forecast the energy that the Sun emits in the form of EUV light to protect our assets. We call this the irradiance. What affects our technology might also affect life in general on other planets. By studying the Sun's interactions with Earth and other planets through irradiance, we may answer questions about the habitability of planets outside of the solar system. Additionally, since the Sun is the closest star to Earth, we have access to an up-close view that helps improve our general understanding of stars that are otherwise observed as distant points in the sky. But our story of perspectives doesn't stop at the Sun's impacts. It is also about how we view the Sun. The Earth orbits around the Sun. Its orbit sweeps a plane that we call the ecliptic. And current satellites are tied to the ecliptic, limiting our view of the Sun to its equator and not its poles. The Solar Dynamics Observatory, or SDO for short, is a satellite that takes pictures of the Sun from the Earth's perspective, and it is the only satellite that measures irradiance. For forecasting irradiance, this is problematic, as we do not know what's coming in the near future, only what is happening in the present. The single viewpoint limits our forecasting capabilities. But speaking of additional viewpoints, the stereo twin satellites were launched with orbits ahead and behind Earth's. But these satellites only take pictures of the Sun in EUV. They don't measure its irradiance. However, a previous FDL project has shown that the EUV irradiance can be predicted from EUV images. Which brings us to the main question of our challenge. How can we observe the Sun and solar radiance from any perspective?
So, as Benoit has explained, we are currently locked onto the ecliptic plane. One solution to this would be to just add more satellites like SDO, but each of these satellites would cost about $1 billion each. And so the solution we propose is to add virtual instruments using machine learning, all for a fraction of the cost. These virtual instruments can be placed at any angle and at any time around the Sun, and they can also measure irradiance, the amount of radiant energy coming from the Sun. More specifically, our goals are to use machine learning to create virtual instruments that can observe the sun from all angles and estimate irradiance from any perspective. And we've done this with our machine learning pipeline called SPIES, which stands for the spectral irradiance of a 3D sun. And we start with the existing perspectives we have from our original 3 vantage points. We will then feed these images to a type of neural network called a neural radiance field, or NERF, that will generate a 3D reconstruction of the sun. More precisely, we've created a NERF that translates the pixels of our images into a model of how much energy or light is distributed across the sun's atmosphere. We can represent this energy from the sun by encoding how much light is absorbed and emitted at a given location within the sun's atmosphere at a given time. And from this 3D reconstruction, we can then generate novel perspectives from beyond our limited viewpoints. We then feed these images from the novel perspectives into another neural network called EfficientNet that estimates the irradiance. And now I'll hand it over to Robert, who will reveal our final results.
So with this approach, we can create the first 3D reconstruction of the entire sun. With only 3 individual observations, we fully recover the geometry of solar features and create observations at arbitrary viewpoints. This means that our telescope is no longer tied to observing from Earth's perspective, but can be moved freely to any position in the solar system. While the original observations are all obtained from a single orbit, we can now even reconstruct the first complete image of the solar poles and view solar eruptions from all angles. With this, our method provides observations that would otherwise require multiple new satellite missions. These novel views can then be used by our virtual instrument that translates EUV images into solar irradiance. But how can we know that our reconstructions represent the physical reality? Our method creates unprecedented views, and there are no direct observations that can be used for comparison. Instead, we focus on the ability to forecast. For this, we build on the delay between the individual observations, where we can compare the predicted solar irradiance with the actual value that is measured when the sun rotates into view. As shown in this example, the predicted irradiance by our new virtual instrument is in agreement with the actual measurement that is obtained 12 days later. With this, we show that our method provides the next generation of space weather forecasts, where we can now determine the total energy at any viewpoint and can provide an early warning several days ahead. And going even further, we can determine the solar irradiance at other planets like Venus and Mars. Especially for future manned space missions, we can now determine solar impacts on Mars. For Earth, irradiance affects our space technology, but for other planets, it can be determining for the existence of life. With our approach, we can estimate irradiance for arbitrary planetary orbits, which gives us a unique way to study habitability for exoplanets that orbit sun-like stars. With that, I pass it on to Margarita.
So to summarize what we have achieved, up until now, the only images of the sun we have available are taken from the 3 satellites, which are in the orbit of the Earth. With our machine learning pipeline SPIES, we are now able to view the sun and spectral irradiance from everywhere in the solar system. And we are now able to have a virtual instrument that can fly out of the ecliptic. And repeating what Ben mentioned earlier, why does this matter? Changing the way we view and study our closest star will not only help protect our assets in space, but it will also help humanity know what to expect as it takes its first steps towards visiting other planets. Thus, it makes it possible for us to connect to other worlds and to the millions of stars out there. Thanks to our partners for the support, and thank you all very much.